Okay, welcome back to the last session of day 3. In this session, we'll take it forward and discuss some of the confusions which you might have and the queries that are there. Okay, okay. So, so we'll start with this application in high energy storage capacitors of these fluorinated materials. So before I go into the details of the applications, we need to know what are capacitors and what are the uses of these capacitors, right? So that's why I want to know how many of you are aware of what are capacitors. Just write y or in the chat so that I know what are capacitors, right? So you get 2 minutes to answer whether you are aware of what is capacitor or not. Just write y or n. Okay, I have started getting answers. Let's see how it goes. I'll hold it for 2 minutes. Okay, so I have seen some answers. 1, 2, 3, 4. Okay, I will ask one by one. Starting from Anjali. Anjali, please unmute yourself.
Yes, sir.
Yeah, can you explain what are capacitors?
Sir, it's a electrical device that can store energy in the form of electrical charge, and it has a SI unit of Faraday.
Okay, and what are the end use of the capacitors? Any idea? What are the application where these capacitors are used? That's why I wanted to know.
Sir, it used in ceiling fan.
Okay, anything else? Any big devices or something? Anything other than ceiling fan? Can you think of? Take your time. Any other application of capacitor apart from ceiling fan?
Sir, inverter
Oh,
may be used.
inverter. Okay, fine. Let me ask others also. Sahaj, if you can please unmute yourself.
Yes, sir.
So what are capacitors? Can you explain? What is your understanding?
Sir, capacitor is an two-terminal electronic device used for the energy storing purpose. And sir, I think you have asked मतलब, a big example. So I think, sir, in 1D graph generator we use na. I'm not pretty sure, but I think I have read it in electrostatic.
Okay, let me ask Navtej. Navtej, what is capacitor and what are the use of this capacitor?
Same definition. Capacitor stores charges. It's a bi-terminal electronic device. Fine. Units are capacitance, which is measured in Faraday. Its capacitance and uses are like uh, IR sensor based circuits. I have used capacitors in one of the project. And
Okay.
secondly, it is used in all right in ceiling fans, maybe in Van de Graaff generator, in rectifiers also, in step up and step down transformers also, and in filter circuits also. Basically electronic part.
Okay, fine. So now can you explain what are can do you have any idea what are high energy storage capacitors? Navtej, can you think of
I
something?
th- yeah, the
What are high
capacitors which would
energy
have
storage
high
capacity?
the capacitors which would be having high capacitance which could uh, store large amount of energy and charges for appreciable amount of time without any leakage.
Okay, it's fine. So we are talking about high energy storage capacitors. This capacitor mostly, majorly, broadly, energy storage devices are called batteries. Solar energy and many energies are stored in batteries, right? So we'll try to understand what are separators and what are binders and what are the use of these materials in this battery, because these are in the same line. If you consider these battery separators are PVDF or polyphenylidene difluoride, this is a molecule which gives the required characteristic of a separator in a battery cell. And there are some copolymers such as this one, um, this one, poly-VDF co-TRFE, that means poly-VDF copolymer with trifluoroethylene, poly-VDF copolymer with HFP means hexafluoropropene, copolymer with CTFE or chlorotrifluoroethylene, all those things. Yeah, Navtej, you want to say something?
So what is this 273 in the scale braces ahead
These
of
are the
PVDF?
okay. These are the references in this reference, cross reference. So this
Okay,
is
sir.
taken
Okay.
from a source. Source material is energy storage material. This is cross reference. Okay. Now we come to surfactants, right? So my first question in surfactant is, how many of you are aware of critical micellar concentration? Write Y or N in the chat option quickly. How many of you are aware of critical micellar concentration? Okay, so my question was, are you aware of critical micellar concentration? I have some answers. I will start with Anjali. Anjali, please explain what is CMC. Anjali, if I
Yes,
yeah, please, yeah. What is CMC? Can you please explain?
sir, there is a fixed concentration for each missile, below which it behaves like a normal electrolyte, and above which it behaves like a colloid. It is known as the critical micellar concentration. The value of CMC is 10 to the power minus 3 mole per liter for aqueous solution of soap. And
Okay.
the temperature at which the conjugated colloid behaves like a colloid, it's called Kraft temperature.
Okay, let me ask Navtej. Navtej, can you explain what is CMC?
Critical micelle concentration, there will be no micelle existence. Above that concentration, micelle formation starts. And I think the temperature at which this critical micelle concentration exists is known as critical micelle concentration temperature. That's known as Kraft temperature.
Okay, great. That's a really elaborative answer. Okay, so that's a good starting point. I can now explain. So see, there are a lot of surfactant. Let's say lauryl sulfate is a surfactant which is present in your shampoos, sometimes in conditioners, in soaps, and all those things. If you check the labels of your shampoo, soap, conditioner, detergent, you will find that this kind of sulfates are always there. Now we are talking about fluorinated surfactants, right? What is the use of fluorinated surfactant? They are surfactants, but added to this, they are stable also. They are stable at higher temperature. This perfluorooctanoic acid or PFOA and perfluorooctane sulfonic acid PFOS are very good fluorinated surfactant. They are much more efficient compared to their hydrocarbon counterpart because normally used surfactants are hydrocarbon based. They contains CH bonds and they contains the polar head group and non-polar tail group. Any surfactant molecule contains a polar head group and non-polar tail group. This molecule also contains that, but added to that, these molecules are very efficient in their property, right? But with these advantages, there are a lot of disadvantages. To understand the disadvantage, I need to start with PTFE or polytetrafluoroethylene, which is also known as Teflon, right? Let me ask, how many of you are aware of Teflon? Just write Y or N so that I know where to start from. Just write Y or N if you are aware of Teflon. Okay, so let me see the answers. Okay, great. So everyone is aware of it. Okay, so now I will explain why I am talking about PTFE or polytetrafluoroethylene or Teflon. So Teflon or polytetrafluoroethylene is used as a coating material in cooking utensils. All the non-stick cooking utensils contains Teflon because oil does not stick to it and the cooking gets easy. Oil will not stick to it. But the problem is the cooking temperature which we generally use, it is very high. So PTFE is stable up to a temperature of 380 degrees centigrade. But just sometimes we cook above 380 degrees centigrade also, and at that temperature Teflon gets detached from the surface and it accumulates in our body. So they are called bioaccumulable chemical, right? So they go and deposit in our stomach and they can cause cancer also. Similarly, these surfactants PFOA and PFOS, because they are used sometimes as a emulsifier also. Lot of surfactants are sometimes used as emulsifier similar to that, and they are sometimes used as a food preservative also. This can go and accumulate in our body, and this accumulation can lead to cancer or many other diseases because they are very toxic. So there have been extensive research to find safer and less hazardous alternative to such surfactant. But this alternative surfactant also should contain fluorine because hydrocarbon based surfactant will not give you the properties which fluorinated surfactant can give. But the problem was of PFOA and PFOS was that they are highly bioaccumulable. So people tried hard to get non-bioaccumulable surfactant. So one of the alternative which was reported is this one, this molecule. If you look closely, this part of the molecule COOH is the polar head group, and this part is the non-polar tail group containing fluorine. This molecule can form micelle, and this micelle can lead to different properties also. Now there are some high performance elastomers which I would like to mention. There are many companies which work on this kind of topics. There are companies such as Daikin, there are companies such as DuPont, Oshimont, and Arkema, Solvay, and all those things. They work on this kind of topics. These materials, high performance elastomers, generally contains very low glass transition temperature. Now I want to ask how many of you are aware of what is glass transition temperature? Can you answer by saying yes or no in the chat? How many of you are aware of what is glass transition temperature? Just answer. Depending on that, I will explain. Answer by typing Y or N. Okay, so please answer quickly so that we can move. If you don't know, just write N so that I can start from basic, right? Because I need to explain it. Glass transition temperature. We'll wait for a few more seconds and then move ahead, I think. Okay, so let me ask Anjali first. Anjali, if you can answer, what is glass transition temperature?
Yes, sir.
Yeah, try.
Sir, the temperature at which the polymer undergo the transition from glassy state to rubbery state. This is
Okay,
known as glass transition temperature, TG.
TG. And any idea how it is measured? How TG is measured? Any idea?
Actually, no, sir, at that much I don't know.
Okay, no problem. Let me ask. 1, 2, 3. Okay, Naftej, please unmute yourself.
Yes, sir.
If you can
That is the
explain
same definition.
how
TG,
it is
the
measured.
glass transit. Sir, no idea about measurement. We can simply heat a glass and see when it will convert it into amorphous and note that temperature, I guess.
Okay, I will. That is a smart answer. I will explain. So glass transition temperature definition part is perfect. So there is an instrument called differential scanning calorimetry (DSC). So that measures the glass transition temperature. As Navtej correctly pointed out, in this instrument, what happens? You take your sample in a closed vessel. So there are small pans. You put your sample, you put another pan, and you slowly heat the sample up, right? While heating up, the sample will undergo the phase transitions, and from there you make it. Now, one thing you need to remember, whatever sample you take, this sample might contain some solvent molecule because they are prepared chemically. It might contain some water molecule also. So there is a thermal history of the sample. So what researchers does, they first heat the sample, first heating, that eliminates the thermal history. They don't take any data from the first heating. Then they cool it down. Basically, they chilled it down. So let's say if the heating is from 25 degree to 200 degree at a rate of 10 degree centigrade per minute, after reaching 200, they will chill it down to 0 degree at a rate of probably 200 degree centigrade per minute. And then in the second heating, they will take the data. Because in the first heating, all that entrapped water molecule or solvent molecule will go away. Sorry. And in the second heating, you get the real data. 1 minute just. Sorry. So in the second heating, you will get the real data if there is any phase change in the sample. If there is a phase change, it will indicate by showing a transition is in a trace, and from the transition, you can determine the glass transition temperature. You can even determine the onset of glass transition temperature at a temperature on which glass transition starts, and the end point of the glass transition temperature at a temperature at which glass transition stops. Right? So broadly, whatever you explained, Naftej and Anjali, it is correct, but I just tried to give you the technicalities. So let me go back to the topic. So these materials, if you consider here, these materials preferably exhibit low glass transition temperature. Low glass transition temperature means that this material is fluid at ambient temperature, at or near ambient temperature. Like if you take silicone oil or any viscous fluid, these molecules has low glass transition temperature. And if you take polymethyl methacrylate sheet, that molecule has a glass transition temperature of 100 degrees centigrade, because that molecule, for that the molecule is the material is solid at ambient temperature, and then when you heat it up at or above certain temperature, this molecule will exhibit the transition. So these materials are prepared using ITP or iodine transfer polymerization. Remember, in ITP you need a bond between carbon and iodine. This bond breaks, generates the radical, and subsequently polymerization take place. And there is a company called DuPont, which is now known as Chemours, and there is a company called Osimont, which was acquired by a company called Solvay, and it is now named Solvay Specialty Polymers, and they have taken care of this field of this synthesis of this kind of material. These materials are used in high resistance coating, O-rings, which I discussed. Gaskets are used basically, if you can think of if you think of a pressure cooker, inside a pressure cooker there is a rubber band, right? So this rubber band is called a gasket. In any vacuum line or wherever high pressure is required, people use these gaskets, and these gaskets for automotive or aerospace industries needs to have a very high glass transition temperature and very high degradation temperature. So I will take a minute to explain another concept called thermogravimetric analysis. Right? Before I explain, I would like to know how many of you are aware of thermogravimetric analysis or TGA. Just write Y or N, and accordingly I will explain in the chat. I will wait for a minute. Okay, so I have found the answers, and I could see it's a mixed bag. So there are no. So I'll explain. Thermogravimetric analysis or TGA is a technique which measures thermal stability of any material. So if you take a material and start heating it up, this material will start degrading. If your molecule contains carboxylic acid, then carboxylic acid will be eliminating CO2, and then the molecule weight percent will go down, right? So with increase in temperature, the molecules start degrading, and this property is measured by thermogravimetric analysis. So if a molecule is stable at higher temperature, that means it is thermally more stable. That is the basis with which we will move forward. So we basically discussed two techniques. One is differential scanning calorimetry, which can determine glass transition temperature, and we also discussed thermogravimetric analysis, which determines the thermal stability of a molecule. Thermal stability of a molecule is determined by TGA. It determines the onset of the degradation temperature. Glass transition temperature is determined by DSC. It determines onset of the glass transition temperature. That is, TG is the glass transition temperature and TD is the decomposition temperature. For for the better understanding, people use TD 10% as a reference. TD 10% is the temperature at which 10% of the molecule is decomposed. Okay, so if there are any confusion on this point, please ask question. I will wait for 2 minutes because without understanding TGA and DSC, it is difficult to move to the next part. Okay, so I could see Navtej is having a question. Navtej, please unmute.
Sir,
Yes,
10% PGA. 10% means 10% of the compound is decomposed. This should be
yes,
different for the different compounds. How can we take it to reference? Or
that's a
on what
very
basis
good
we take
question.
on the different conditions of the environment, this temperature, all right, the temperature will vary also on the different environmental temperature, pressure, etc. conditions.
Okay, so your answer is sorry, your question is very nice and very good. I will try to explain. So thermogravimetric, and I thank you that you asked so that I can explain in detail. Thermogravimetric analysis is performed under the presence of externally added gas. The gas is either nitrogen or oxygen. If your material has a chance of getting oxidized, it is made measured under oxygen, right? So this is a controlled environment under nitrogen or under oxygen, right? So under this condition, if you control the ramping temperature or ramping rate, so you will go from 25 degree to 800 degrees generally, and you go at a steady speed, let's say 10 degrees centigrade per minute or 20 degrees centigrade per minute. Generally people run it at 10 degrees centigrade per minute. So if you run, let's say, three samples A, B, and C at 10 degrees centigrade per minute under nitrogen from 25 degrees centigrade to 800 degrees centigrade, then these three different sample will have different TD 10%. That is the temperature at which they will degrade 10%. Clear? So that is defined, and these values are reported also. Under this condition, these values are reported also, and there is always a ASTM standard protocol following which we run any analysis. And this standard protocol, this set protocol, is so nicely done that if a literature paper writes that TD 10% of PMMA under nitrogen at a ramping rate of 10 degrees centigrade is, let's say, 60, that will always be 60, whoever repeats in whichever part of the world. Navtej, if there is any
Sir,
remaining query.
now one more question I am having that
Yes.
recently in the crystal engineering discussions we found that if we consider any of the crystal formed crystal, if we suppose synthesize the crystal in IIT Bhilai and send it for the further studies in 2 3 different countries, and if we try to recreate that crystal in that conditions, in that places, even if we create with the same absolute precision, but the properties and the form of the polymorphic form they might differ. So how can we say that if a literature paper is noting that 10% TDA value is just 660 or something, so it would be 60 if we recreate that thing.
Okay, so this question is also very nice. Now you need to understand what you are understanding in crystal, what you are analyzing in crystallization process. So basically, you are synthesizing the material in three different places. In case of TGA study, you are not synthesizing the material. The material is already synthesized. The material is already fixed. You are analyzing the material under a very set ASTM standard protocol. Following everything is same, any part of the world, it has to give the same result. That's why TD 10% or even for that matter glass transition temperature are reported in polymer handbook, because samples, same sample under the same analysis condition using the same instrumental parameters and ASTM standard has to give the same result, right? Because you are not changing the synthesis process. There you are changing this, you are doing the same synthesis in different parts of the world where the environment, relative humidity, or the moisture content in the media may be different. If you do the synthesis under restricted or controlled environment, which is same for all the cases, then the result will also be absolutely same. Yes. Any
Sir,
further query?
this is again a catch that if we do
Huh.
it with absolute precision, with the same
Huh.
humidity, same something isolated medium, even then there is difference in the form or properties uh,
Huh,
in
because
that
because
crystal synthesis.
it, it can be different because there will be something changing, right? The synthesis process, same sample cannot be repeated twice. That is a bottom line, right? If you prepare a sample in the second time, you might not be preparing the same sample. There will be some variation because there are so many parameters to control, including how you are adding the ingredients. Someone might add dropwise, someone might add as a blast, boom. So these things will change. That's why it is changing. But in the analysis
Now, if
part, your material is not changing. Material is same. You are just analyzing it using a set guideline. So that has very very rare chance to change.
yes, sir, this is
Oh, fine.
convincing as explained.
Okay. So Anjali, please unmute.
Yes, sir.
Yeah, your query.
Sir, my question is that what are the application of TGA and what are those factors which affect the TGA?
Okay, so I'll explain. So TGA or thermogravimetric analysis is a instrumental technique. It is used to measure the thermal stability of any material ranging from metal, ceramic, polymer or any other organic or inorganic molecule. So it just determines how stable your material is, and this property is very very useful. Let's say if your material start decomposing at 60 degree, you cannot use that material as a coating material for exterior paints, right? Outside the building you cannot use it because sometimes the temperature can go up to 60 degree. You coat the material, you take the material, use it as a paint, and in very hot summer of our place or in your state, it will just melt away. So that is not acceptable. So this kind of guidelines TGA can provide what will be the operating temperature of your material. Is it clear?
Yes, yes, sir.
Okay, so I could not don't see any other query, so I'll move ahead. Okay, one thing I should mention here. Just give me a minute. Okay, that this automotive and aerospace industry is a high temperature industry basically, right? Because you are working with liquid fuels which can runs up to very very high temperature, right? And for biomedical items you are working with materials which are very very pure or impurity free or non toxic. In both the cases, after synthesizing your polymeric material, you need to ensure that there is no catalyst leaching. Generally, whenever we use homogeneous catalyst, there is always a problem of catalyst leaching, right? Now I have to ask again, what is catalyst leaching? How many of you are aware of what is catalyst leaching, right? Y or N in the chat option. That what is catalyst leaching? If you are aware of, write Y, otherwise you write N. Okay, so let me see what is going on. Okay, Narendra said he doesn't know. Navtej knows. Okay, Navtej, can you please explain what is
The
catalyst
catalyst,
leaching?
we
Yeah.
use catalyst first because it increases rate of reaction. Second, that it is regenerated again at the end of reaction. But in some cases, there might be a possibility that some amount of catalyst is not yet regenerated and is gone in the product side also. So that is called catalytic leaching, I guess.
So this is good for the reaction or bad for the reaction? If you can elaborate.
This is bad for the reaction and bad for the use of the product in further applications also. Because if the with the repeating cycles of the reaction, in this way the catalyst will leach, and at one time we will not be having any catalyst. Secondly, if we are using catalytic leached product for further application, and if in the case that catalyst could like in biomedical items, if it is poisonous or bioaccumulative, so that is also hazard for us.
Yeah, that's a good answer. So basically, what we have to do that we have to remove this catalyst leaching. So there are multiple ways to do that from the final material. One way is to use heterogeneous catalyst, the catalyst which can be separated very easily after the reaction, right? And it doesn't leave any trace of the metal in the product. Other Another way is to have efficient catalyst separation strategy, but always the use of heterogeneous catalyst preferred over catalyst separation strategy, because that is very costly. If you, let's say, if you use iron chloride as your catalyst in a soluble media, what will happen after the what will happen after iron chloride is used after chloride is used in the reaction media? It will leach in the final product, the metal iron, right? And it is difficult to separate your metal. Your final polymer will be color, toxic, and useless for the end application, and that is not good for the end application. Okay, so let's go ahead little bit at this point. Okay, so in this slide, before I go ahead, tell me what is, if you are aware of what is anti-fouling material, right? Yes or N? Y or N in the chat. If you are aware of anti-fouling material, write Y. If you are not aware of anti-fouling material, write N quickly. So let me see. Okay, fine. So I will explain. So generally, whenever what is foul? Let's first understand what is fouling. Fouling means growth of a biofilm on a surface. So if you have seen, if you leave in any object or any living object outside in the environment, there will be fungal infection. So fungal infection is basically growth of film. If you see the ponds also, there is growth of algae and all other things. So these are film formation. This biofilm formation is fouling, right? So now if you wish to protect your device from the marine environment, especially the ships and all those things, what you need a material which will be anti-fouling, right? So this material will basically protect the metal, so that this metal does not get damaged under the sea environment. Now if you think closely, what is there in the sea environment? The sea environment contains lot of salty materials. These salty materials will lead to more fouling, right? So what people does, they make anti-fouling material based on polyvinylidene difluoride And this polyphenylene difluoride is stable at harsh conditions, and this does not allow protein molecule to grow, so that your surface is protected even under exposed environment. Is it clear? If there are any confusion, you can ask. If you want me to repeat also, please raise your hand and ask. This is a tricky concept, I understand. Fouling and anti-fouling. If there are any confusion, you can ask question, unmute and ask question, or you can just raise your hand so that I can repeat it.
Sir, can you please repeat once again?
Yeah, sure, definitely. Okay. I will repeat. So before understanding anti-fouling, let's understand what is fouling. Fouling is formation of biofilm on a surface. Why this biofilm forms? Because when you keep any material in outside environment not protected, there are small protein molecules, or there are small molecules which will grow on the surface, right? And these are some kind of fungus, or can be some kind of bacteria or whatever. They will foul the surface and there will be biofilm formation. This biofilm formation will damage the performance of the material, will generate toxin, generate foul smells, and make the material useless. To protect these materials for external use, what scientists have done, they have protected this material using anti-fouling material. So what are anti-fouling materials? Anti-fouling materials are materials which does not allow growth of biofilm formation. It will protect the material, it will not allow any film formation, so that the material can retain its property for higher time. Is it fine? Any other remaining query?
Sir, what are photocured materials?
Okay, so that is a good question. Okay, let me explain. So, okay, I hope all of you are aware of this pericyclic reaction 2 plus 2 cycle addition. If your material contains a olefinic molecule, right? If you have multiple materials containing olefinic molecules, then if you induce light, there are light induced 2 plus 2 cycloaddition, and this 2 plus 2 cycloaddition can lead to cross linking, right? Let's consider if you have a 4 amstar molecule containing olefin at the end, multiple 4 amstar molecule, and if you shine UV light into it, so there can be UV induced cycloaddition reaction leading to cross linking. That's when this material is called photocured or
Then what
photocross
is
linked.
difference between photosensitive and photocured?
Okay. Technically there is no difference. If you allow a photosensitive material to be in presence of same molecule, similar kind of molecule, then it will be photocured basically. That is the understanding.
Uh, if I am not wrong, catching the point, uh, the paper which was published by your department on the self-healing polymers, was that using this type of thing?
Yes, yes, yes. That was using this kind of thing. That was using coumarin moiety, which undergoes photocuring when we shine 365 nanometer light or UV light, that undergoes 2 plus 2 cycloaddition reaction and generates a cross-linked network. But that was reversible when we shine 254 nanometer light, the cross-linking breaks down. So basically it was reversible 2 plus 2 cycloaddition reaction in that case.
Now, sir,
You can
the
say
catch is
photo cured and photo non cured. Yeah, please, Navtej.
now the catch is that why was it called self-healing if we are inducing it by using the particular wavelength of UV light? So it is induced self-heating healing polymer or self-healing polymer.
So it was written, I think, photo induced self healing.
Okay,
If
fine.
you,
Thank you, sir. Then fine.
ha, There are two types of self healing. One is induced self healing, because you are not touching the material, you are providing a stimuli. So there is a induced self healing, and another one is autonomous self healing. Right? Autonomous self healing generally happens in living body, and externally there are induced self healing, unless you are using thiol disulfide dynamic exchange. I think in one of the paper we used thiol disulfide dynamic exchange also to achieve self healing. That was autonomous. Okay. So if there are no
Yes, sir.
query, I will move on. So these are gel polymer electrolyte for lithium ion batteries. The structure is really complicated. If you have a look at this structure, this is tetraamster molecule, which lead to this kind of structure. Tetraamster molecule, which lead to this kind of structure. Okay. So at this point, I would like to know how many of you have worked on the molecule. Amul, did you share the image? Yes. So one of my student might have shared an image of a molecule which we were supposed to discuss, right? How many have you looked at it so that we can discuss? Can you write yes or no if you had a chance to look on it? The molecule which was supposed to be environment responsive also. Just write yes or no so that we get a chance to discuss it today. Let me see the answers. Based on that, I will discuss. So my query is, we shared structure of a molecule, structure of a polymer, which is temperature, pH, and probably environment responsive. Did you get a chance to look at it? How this works? Because I remember we were supposed to discuss it. Okay, fine. So I will pull up that slides so that we can discuss. Just hold on for a minute. Huh? Okay. So if you can see the screen, I tried to pull up the slide, which the image for which was shared. So I will explain what is going. I will try to explain what is going on in this molecule. But first of all, I would like to hear from you what you understood, and then only I can explain. Right? So we'll start randomly in a random order. We'll start with Swaminathan. If you can unmute and explain why this molecule is pH, temperature, and environment responsive. Let me see. Swaminathan is there. Where is the participant list? People. Yeah. Okay, no, see, he is not there. Fine. So let me go to Sandipan. Sandipan, please unmute yourself and explain
Yes,
why this molecule is pH, temperature, and environment responsive. Yeah, Sandipan, your answer. Okay, so we'll move on. So we'll move to Anjali. Anjali, please unmute yourself.
Yes, sir.
Yeah, can you explain why this molecule is pH responsive?
So by definition I know, but by seeing this both images I didn't know.
So by definition, what is your expectation? How why a molecule should be pH responsive?
Sir, they might be respond to a pH solution by undergoing structural property changes and many other properties changes so that it may called as pH sensitive response.
So does this molecule have any molecule which can respond to pH? Can you find it out whether this molecule has anything which respond to pH?
Sir, I think amine bond, imine bond.
Okay, so let me go to Sahaj. Sahaj, please unmute yourself.
Yes, sir.
Did you have a chance to look at this molecule?
Sir, I have yesterday Amol Bhaiya shared, then I see this, and before that I
So
didn't.
no problem. So after that, did you get a chance to look at? Can you explain why this molecule is pH responsive?
I think due to sir presence of nitrogen, it work as a base, and uh, two groups are of nitrogen. That means it is of basic character. So I think that's why it is pH responsive. Maybe.
Okay, so let me ask Navtej also. Navtej, please unmute yourself.
Yes, sir. Sir, the
So
part
why
which
this
is
mol?
pH responsive, I guess that at higher pH it will exist as NH4. One H will also attach and N positive cation will exist. So due to that, the extent of hydrogen bonding, which was earlier being formed by nitrogen in the polymer, will be weakened. So one thing, this is pH responsive, and the part which is temperature responsive, I guess that as we can see, this is whole hydrocarbon part this side with nitrogen, and this is having van der Waals forces of interaction at higher temperature. These forces will weaken away, and due to which the binding again change with temperature. So I just know pH and temperature. I don't know whether they are correct or not.
They are more or less correct. Can you explain the last part? Why this is environment responsive?
I searched a lot about this. I found only this, that those materials which are uh, responsive to the certain environmental changes, I guess, but I didn't find the examples of those stimuli which would come under this category.
Okay, so let's closely have a look at what this functionality is. Then only the answer will come. So if you closely look, what is this? Can you name what is this functionality? This molecule? 1 minute. Give me 1 minute. Let me draw it correctly. Okay. So pointer pin. So can you name what is the IUPAC name of this molecule? This part.
Not sure, but might be imidazole.
Imidazole.
No, no,
Sure.
I'm not sure. No, no, not that.
So this is called benzofurajan, right? So this is in this part is environment responsive. This benzofurajan part, because this benzofurajan derivative is polarity responsive. So at a high polar solvent, it this oxygen molecule gets protonated and it becomes colored, and at a low polar solvent with low polarity, this is not colored. That's why this is environment responsive. So that using that color change, you can determine whether your molecule, whether your media is high polar or non-polar. So at a highly polar media, this will be colored. At a low polar media, it will be non-colored. And I will also explain the temperature responsivity because some of you could not answer. So this PNIPM is temperature responsive, which I explained earlier. At a low temperature, it is soluble. At or above a certain temperature, it becomes insoluble. That is called lower critical solution temperature. And this left part, which is pH responsive, is basically tertiary nitrogen part that becomes protonated and become quaternary ammonium, and that's why it becomes pH responsive. So that was the explanation. Okay. Okay, so there is a query. Let me see who has raised the hand. Just to give me a minute. Okay. Okay, there are two hands basically. Anjali, you can go ahead first.
Sir, can you give any other example of environmental responsive which will be?
Definitely. Definitely. So there are some molecules which can respond to carbon dioxide also. So let's say if you have a polymer containing quaternary ammonium hydroxide, right? Then this molecule will be carbon dioxide responsive because this molecule can trap carbon dioxide as ammonium bicarbonate, right? So this is also environment responsive. So if you have a molecule containing quaternary ammonium hydroxide, this molecule is environment responsive because this molecule can capture carbon dioxide as ammonium carbonate, ammonium bicarbonate. Is it clear?
Yes, sir.
And I think, let me see there if there are any other query in the chat. Just give me a minute. So the name. So benzofurajan. That name is benzofurajan. Okay. So I think at this point we'll close the tutorial, and I thank you for joining. And tomorrow's lectures and tutorial will be delivered by Dr. Bruno Amaduri starting from 3:30 p.m. And okay, so there is a query. Navtej, please.
Sir, as we know that chlorofluorocarbons are harmful, they are non-eco-friendly. They deplete the ozone layer with a certain mechanism. So what about the fluorinated polymers? Are they eco-friendly?
So that's a good question. So fluorinated polymers, so I can say chlorofluorocarbons are negative, fluorinated polymers are neutral because you can make these polymers eco-friendly. PVDF is not biodegradable, but if you include hydrolyzed molecule, if you include functionality which can be hydrolyzed, then PVDF can also be made biodegradable. So yes, fluorinated homopolymers are not eco-friendly. They are non-biodegradable. They remain as it is for ages. But if you make a copolymer out of them, and if your copolymer contains hydrolyzable group, then they becomes hydrolyzed. Then they become biodegradable, as we discussed while discussing the phosphonated fluoropolymer part. Is it
But
fine?
even after
Ah,
being hydrolyzed, the remaining two parts of the copolymer after hydrolyzing, one of them would also be having fluorinated part. Then it would again be non-biodegradable.
you are correct. Then I will explain you how biodegradability work. I will encourage you to read it from other sources also. For brevity, I will explain. It is like unzipping. So if you have a bag, if you have a zipper, if you open the zipper, you have to take it to the last point to open the zipper. But that is not how biodegradation works in the polymer. You just need a trigger and the zipper will automatically open. You understand? So that trigger is the hydrolyzed moiety. That trigger is the moiety which can be hydrolyzed. And even these fluorinated polymers, they can undergo dehydrofluorination. There are a lot of instances that this polymer can undergo dehydrofluorination, but that is not the preferred path. Preferred pathway is you introduce some hydrolyzable functionality, and based on that hydrolyzable functionality, this they will just unzip. They will undergo degradation from start to end, like an automated zipper of a bag.
Okay, sir. Thank you.
Okay,
Fine now.
thank you for attending the lecture, and I will close the session. We'll see you tomorrow for Dr. Bunu Ahmed's lecture. Thank you. Bye.